Hello everyone and welcome to my talk. This is a rehearsal talk, if you will, or a recording of the talk that I will be giving at the German workshop for medical imaging, BVM, in Braunschweig in a couple of days. And I'm just using this opportunity to rehearse and also record the talk for you out there. My name is Mark Opelville and I'm part of the research group Deep Microscopy, which is a joint group together with Katharina Breininger. And today I will be presenting something about atypical mitosis, how to detect it, and what to do with that knowledge. So let's get right into it. What is mitosis again? Mitosis is the process of cell division, so something that happens really regularly in our organisms all the time, but is well regulated. And we have different phases in the mitosis, and don't worry, I will be talking about all of them very briefly to then get into the why mitosis can be atypical. So let's start with the first phase, or which is not actually a phase of mitosis, but it's actually just what we see here. So we have on the left hand side the cell itself, and then we have, let me just get my pointer here. So we have the cell itself here, and then we have the corresponding histopathology H&E stained image. And what you can see clearly here now is the cell nucleus, which is of course here stained by the hematoxylin in dark violet, we could say. And then we see the centrosomes, which are also cell organelles that help organize the mitosis process. And once we start with the mitosis phase, then we can see that those centrosomes are pulled towards opposite ends of the cell, and they help to build this mitotic spindle. And at the same time, the chromosomes, which have been replicated beforehand, are now condensing into so-called chromatids. And this is also what we can already see, although not distinguished really well in the histopathology H&E stained image. Following up the next phase, the centrosomes get pulled further to really opposite parts of the cell, and they attach also to the now free kind of chromatids. So what I didn't mention here is that those are now, of course, like always in pairs. So one pair for the new cell, for the new daughter cell. This phase is called the so-called pro-meta phase, and it's the second phase of mitosis. And we cannot really distinguish it so well in many images of H&E, but it becomes clearly visible as a mitosis. Moving on, we follow to the meta phase, and then we can see that now kind of these little mitotic spindles, they are pulling with some force on those chromatids, and this means that they are now building this very well regulated, beautiful plane, which is this what we can see in the H&E image really well. Also, if we move the whole situation just by looking from the top, I mean, now we looked basically from the side, and now if we're looking from the top, then we can see that this whole thing can also look very differently. So it can also look like a ring because of the geometric arrangement of that. It's the same thing, it's still the meta phase of mitosis. Moving on, we're coming to the anaphase. The anaphase, these like pairs of chromatids get split apart by increasing forces on them and get pulled towards the opposite ends of the cell. This is something that we can clearly distinguish in the H&E image, as you can see on the right hand side. Moving on further, we can see now that again, some nuclear hulls are being built where the chromatids then are collected, and this is then called the telophase, and it's actually the first phase that clearly, where we have clearly like two parts that are condensing again into what will then, in the next step, be two cells. So that's the mitosis, that's the cell division process, and that's how it should work normally. Now, when I say this is how it should work normally, there's also a abnormal, and that's what we call the atypical mitosis. So yes, this can also go wrong. And what happens then, we will be talking about that now. Now, for example, if we take a look at this phase here of mitosis, or maybe also metaphase or anaphase. So it could be actually any of them. Then it could be that we have now all of a sudden 3 centrosomes in the cell, which all help or want to build some kind of mitotic spindle, but all attached to some kinds of chromatids. And then we might have this tripolar shape in the H&E image that you see here on the right hand side. Now this clearly looks not as the original mitosis, but it is clearly also a mitosis. So the problem here is that actually the phases are now becoming hard to discriminate because they are now no longer typical. So let's have that in mind for what follows up next. And then if we have also, for example, in the anaphase, metaphase, there's another phenomenon that could occur, and that is that chromosomes are not being attracted or not being attached to the new cell hulls or not being included by the new cell hulls. So what we call like chromosome lagging. So they're still in the cell and they have not yet been completely assigned to one of the daughter cells. Yeah, so these are 2 things, and of course this is clearly what is happening if the whole cell division process gets out of range, and this is what's happening in tumors. So that's also the relevance of that, and in particular there have been multiple studies suggesting that the presence of atypical mitotic figures in an independent and highly is an independent and highly prognostic marker for malignancy. So one of the studies was in 2018, one of them in 2021. So you can see that this is fairly recent insights that we got into the tumor pathology here. However, there has not been yet any automatic detection which could be used in order to investigate this on a larger scale, because the atypical mitoses are much rarer than the normal mitoses. So this is what we set out to do. So we set out to do an automatic detection of mitotic figures, an automatic subtyping of them into typical and atypical, and also into the phases. Now, when we do this, we typically go first and collect a data set, and we built this work on top of 2 data sets that were already available, which are the 2PAC16 and the MIDOC 2021 data set. Both are state-of-the-art mitotic figure data sets, which have been categorized by 3 pathologists at least, and we then took those and showed them to 2 pathologists, Taryn Donovan and Christoph Bertram, who participated in this research, and asked them to please assign the respective typical shape, or if they are atypical. And what we can see here now is a confusion matrix between those 2 experts. And what we can see here is that the agreement isn't great. It's like 75% agreement. I mean, it's still not nothing, but it's, I mean, if you want to use this for a classification task, 75% isn't really great as a baseline to start with. So that means that we have like an unknown, kind of phase or typicality for almost 25% of the cells. If we wanted to phrase this as a typical object detection problem, then we would run into into a couple of problems. But we can do this. So, I mean, in principle, the atypical is hard to subdivide into phases, right? So that's why we just say, okay, let's just take atypical and then the typical phases. And then we have another category, which is unknown, right? Which is on the right-hand side. So, yes, we could characterize this as a multi-class object detection problem, and we will also do this as our baseline. However, this has a couple of problems. First of all, the unknown mitotic figure is a non-disjunctive class. We cannot leave it away because, I mean, we still want to have an object detection and it's still mitosis, so we want to detect it, but we cannot subcategorize it in any way. So this is a bit of a problem if we have this kind of flat representation of classes. And each individual phase is also not completely disjunctive to the atypical cases, because of course, as we can saw on the chromosome lagging, there is actually overlaps between those phases that are not clearly distinguishable, but they are there. So in order to solve this problem, we will go and formulate this problem a little bit differently. And we will formulate it as a hierarchical object detection problem. So where the first hierarchy is the detection itself, then we have the first level and we have the second level. And the level 1 is the atypical versus normal, and then we have the level 2, which is the different phases. The good part is that for each of those levels, we can also now assign an unknown sublabel, and we can use that for the next following deep learning pipeline. So this is how we will do this. First of all, we took as a baseline the so-called FCOS, fully convolutional one-stage anchor-free object detection approach, and we extended it by 2 subclassification heads, corresponding to the 2 subclassification levels that I described earlier. We trained the network on the MIDOC 2021 dataset, and we evaluated it on the 2PAC16 dataset, so we have a really disjunctive set of datasets. As a loss function, we use a generalized intersection over union dependent focal loss, as we also would do for the FCOS, but we gated it by the subclass availability for the respective subclasses. All right, so let me come to the results already. And talking about the results, I need to first of all tell you that we have now 2 different kinds of result evaluations that we're looking for. First of all, the detection part is independent of the subclass, because for sure this detector should find all mitoses. So I mean, it's also a very interesting question and decisive question, like how many mitoses are there. So detection overall is one of the most important metrics that we have. We will measure this as average precision and recall. And then we have the subclassification, which we do as a ROC area under the curve, and which is these 2 levels, atypical normal and level 2 pro-metaphase ring shape, metaphase, and anotalophase. Right, so let's go into the numbers, into the evaluations, and if we do that, then we find that the average recall is really high, so 0.95. The average precision is not that high as we could or would have hoped for, it's 0.55. However, this in our view relates to a possible domain shift between the data sets. Simply put, these are from different clinics with different stain environments, so this could have played a major role, and we didn't account for that. Then we have the other question of subclassification, and here we have AOC values of 0.88 for the hierarchical, which exceeds the baseline, and actually it exceeds also for all the other classification tasks, or also all other tasks. The hierarchical exceeds it. It has been, I think, 5 or 10 runs. I'm not quite sure, to be honest, how many we did. I think I wrote it in the paper, and where you can see here the mean and standard deviation of. Right, so let me summarize my work. So the identification of atypical mitotic figures is actually relevant for tumor characterization, and there is a significant disagreement between the experts. So this poses a problem in the machine learning sense, and the hierarchical formulation that we did in our work here in our paper, this improves the detection and the classification performance at the same time, and this is from our perspective the foundation of what yet has to be shown, which is basically the confirmation of those findings by other authors on large-scale data sets to correlate this with the survival data of the patients. And that's it. Thanks for listening.